A block of mass m, which is 2.5 kilograms, starts from rest and is pulled across a rough floor, by a horizontal rope. There is friction between the box and the floor with kinetic coefficient of friction, basically meaning the friction due to with motion. The tension of the rope is 22 newtons. After moving the box a distance of 2 meters, the box has a velocity of 3.9 meters per second. Okay, what is the WR? WR being the work done by the rope as the block is moved 2 meters. Okay, so this, we just go straight to the definition of work. Work equals integral F dot dr. In this case, force equals tension, and dr, I'm going to say, so this is our picture right up here, I'm going to say the r hat direction goes that way. So, tension is in the same direction as the motion, and tension is constant because they give us an actual number for it. So we're going to rewrite this as F integral dr. This dr here, we can just do an integral dr. You could do it more formally, which would basically be integral of, we're going to say 1 is in there. Integral of 1 is x. Take that from r initial, r final, and you get r final minus r initial. Long story short, this is just the distance. How far this box moves. I'm going to call this delta x. I'll call it delta x. Though delta r would probably be just as, if not more appropriate. So, long story short, work equals force times distance. And this implies a constant force. So we do have a constant force, that's 22, and we have a known distance, which is 2 meters. So 22 times 2, which equals 44. And since this is all done in SI units, we'll have joules. Okay, so possible answers, 0, nope. 44, yes. And then they have negative 44 here. So this is where I'm going to take a second to kind of step back and look and make sure that I got my sign right. So the sign comes from, I know, super incredibly messy. Whoop. Get rid of some of this. The sign from this comes from the equation, work equals integral F dot dr. This is a dot product, and these are both vectors. It's not usually written that way. It is, and you should understand that. So the dot product has to do with the cosine between the angles, between the two vectors. So we have f going this way, we have r going this way, and therefore theta between the two is 0. Specifically, it's not the opposite direction. And so they're the same direction, therefore we keep the positive sign. Therefore, the work is going to be positive 44 joules, not negative. That's the way I try and think of it, and I try and do it in an exceedingly formal way like this, because it's really easy to get those signs wrong, and you don't want to. Another way of thinking of it is if your force is in the same direction as motion, basically the vectors are parallel together, then more than just parallel, in the same direction, then it's going to be positive. If they're going opposite directions, then they'll be negative. Okay, what is the coefficient of friction? Coefficient of kinetic friction, because everything's moving the whole time, except for when it starts, between the block and the floor. So we could look at this in two ways. Well, probably more than two. We could do like an energy balance, which would be very formal about energy potential, energy initial, energy kinetic, initials, plus any other extra energies. Then we have energy potential final plus energy kinetic final plus whatever, some sort of other energies. And we could balance it out and be formal about it. I'm going to be a little bit less formal and try and focus more on being intuitive. So we have a block that starts at rest, and we're adding energy to it. Specifically, we're adding some energy due to the tension of this rope, tension, and then we're also adding energy, which is, taking energy away from friction. So I'm going to look at this. I'm going to start by writing this out as 0 equals energy kinetic. So energy kinetic is 1/2 mv squared. So when we have no energy added to it, it makes sense that we're going to have 0 as our, so we have 0 energy, we have 0 speed. So have just a block right there, do nothing to it, we have 0. So, but if we add to it, let's say we have energy kinetic, and we add some, I'm going to call this work, W, work, and I think they used R for rope, work rope. That's going to be, make it go a little bit faster. And then I'm going to add in, I'm going to say work due to mu. And I'm going to say F for friction. There we go. F for friction. So energy kinetic, and we have work due to rope and work due to friction. Now this one's going to be negative, so less than 0. This one will be greater than 0. So this will make it go faster. This will make it go slower, or to the right, to the left. So what we need to do then is rewrite this. So I'll write this down here. This will be 1/2 mv squared. And this will equal work due to the rope. We already discovered that up here. That's 44. 44. And I'm just going to leave the joules off for now, the units. And then we're going to have work due to friction. So work due to friction, formula for that, work of friction equals integral F dot dr. Force due to friction will be the normal force times whatever your coefficient of friction is. So this will be mass times gravity times mu k. And this will all be dot dr. Integral. So these are multiplying, that's a dot product. But these are also all constants. So we can pull them out. So what we're left with is something like mass times gravity times mu k times delta r. Now, one of the things to note here is the force in this case, force that's going this way, force friction. We have motion going this direction, make a little r, make a little vector thing. They're in opposite directions, so it's going to be negative. So that's something we just have, I'm going to basically throw the signs out and then just put them back in at the right place in the end. That way, it's more intuitive, less formal. So this integral.dr, that's just the distance, so that's going to be 2. So this is going to be mass times gravity times mu k, which is what we're looking for, times 2. Yeah, let's say 2. Okay, so now we're going to, so this is plus, I'm going to change this plus to a negative, mg mu k times 2. All right, so now I'm going to start putting in values. And we're going to try and solve for that guy right there. So let's see here. Put this over, move this guy over there, move that one over there. So we'll have mass, which we know the mass is what? 2.8? 2.8. So we have 2.8, this part's just algebra, times 9.8. Let's say 9.81. Mu k, unknown. 2 equals 44 minus 1/2 times mass, which is 2.8, times velocity squared, which I think they give us the final velocity, 3.9. So we have 3.9, don't forget to square it. Then solving this, change colors, let's do it green, green. Mu k equals 44 minus 1/2, 2.8, so many numbers. Part of me wants to try and simplify this, but I am worried that if I tried to, I would make a mistake. So I'm just going to plug it all in my calculator and hope for the best. I know, it's tragic. All right, so I don't need to switch to degrees because there's no angles involved. Well, the angle's 0 degrees, so it's dot product. We're fine. Don't worry about that. 44 minus 0.5, which is 1/2, times 2.8, times 3.9 squared. I'm going to enter, divided by quantity, 2.8 times 9.81. Whoop, click, click. And we get 0.8266. 0.8266. Okay? Is that a possible answer? Not really. So 0.826, closest is that one, but not quite, and it doesn't feel right. So let's take a look at what we did here. So 44, 3.9 squared, 2. This is what I forgot right there. Whoop, 2. We need an extra 2 down there. So we'll go back to calculator. So I'll do 22.706 divided by quantity, 2.8 times 9.81 times 2, and we get 0.413. Aha! Equals 0.413, which I'm going to say is this one right there. Okay, so take a step back real quick. Yes, that seems right. Take a look at what we did just to kind of encapsulate everything. So we had a block being pulled with friction. We wanted to first find out how much work was done by the rope. That's basically just the definition of work equals integral F.dr. You haven't taken calculus yet. That'll be kind of confusing. For you, that would just simplify it as work equals force times distance. But one of the implications here is that force is constant, and if force and distance are in the same direction, then it'll be a positive number. If they're in opposite directions, then they will be then you'll do negative work. And if they go off somewhere funny, then you're going to have to do a dot product, which is cosine of theta. So we did that. Then we wanted to find out what the coefficient of friction was. So we know how much energy it ends with because we have kinetic energy. They told us how fast it's going. And we know how much energy we add to it through the rope. And we're trying to find out how much energy is taken away through friction, mu k. Now the formula for friction is mass times gravity, which is the normal force. Basically, I have a block sitting here. How much force it pushes down on the ground, times coefficient of friction, mu k. And so then we did some algebra, made a mistake, and after we corrected the mistake, we found the answer was 0.413, which is about 0.41. So I hope that helped, and I will see you next time.